This is Group 1's Uniform Stress Cutter summary. What is a uniform stress cutter? A uniform stress cutter is a device that allows for uniform cuts on a material. So the force applied to the object we're cutting is evenly distributed. We're cutting a cylindrical shape material, so we'll probably have to use multiple blades in order to get an even distribution. A uniform stress cutter creates a cleaner cut and reduces stress on the blade or blades, which makes them last longer.
Alright guys, welcome to SUNY Poly's Additive Manufacturing Lab, nicknamed the 3D Printing Lab because of the 3D printers. My name is Melvin, I'm going to be showing you around here, and we will be producing our cigar cutter. Let's do this. So welcome. The nickname for the 3D Printing Lab comes from the 3D printers that are located inside of here. As you can see, we have a whole lot of them. Let's see how they work. So these printers we have here are Ender 3 S1 Pros. These are a type of FDM 3D printing, which is fusion deficit modeling. They take a spool of material, as you can see on the top right here, this white plastic. This is PLA in our example here. They run it into an extruder, which heats up, in this case, to 210 degrees Celsius, more than double the temperature of boiling water. So I will not be touching that when it's on. And it prints it out in a, much like a 2D printer that prints paper, where the head moves back and forth to put the ink on a piece of paper. This does the same thing layer by layer by layer. It moves up and up and up. Let's take a look at some of the examples of that. So this table here has a lot of example prints of things that have been done in this lab so far. So on the right hand side here, my right, your left, you will see a bunch of examples of PLA 3D prints. PLA is our very general plastic. It is versatile. It can be used for many things, whether it's a model of a boat, something more useful such as a video game controller holder, or even brackets. It is a very versatile material. We can also do things that are flexible, such as these caps using the joints, but sometimes you need something that's a little bit more flexible than that. That is when we turn to materials such as TPU, which is right here. You see this vase, now you see it, now you don't. Now it's right back to where it was. TPU, you can compare to rubber and its properties and the way that it flexes, such objects can include like a doorstop here where it flexes, or even an airless bicycle tire project. So a very small section, obviously. So sometimes though, we don't want flexible, we want that rigid property of PLA, we want it to be even stronger. That is where we turn to ABS. It is strong, it is rigid, it's a little bit more expensive than PLA, but its only other downside is that when it breaks, it does break more catastrophic. So where PLA may just crack, ABS will more similarly explode. So it still can be very useful though. Here's an example of a gear that was made to repair one of the lathes in one of our other labs, which you may be seeing later depending on how our universal stress cutter project goes. But there was a gear on the oil pump that ended up going bad, and it was $130 to purchase and ship, and it would take a few months to get there. This is an example of something that was produced and 3D printed overnight. The next day, it was put into the lathe and worked perfectly. So it's just another one. Moving on from our small SUNY school, I'm sure you've heard of NASA. NASA, up in space, they lost a very specific ratchet. Whether it just floated out into space or they just couldn't find it, maybe someone has it in their pocket, who knows. But they lost it and they needed it, so someone down on Earth, instead of sending a rocket up, designed a CAD file to go up into space and 3D print up there. So it is just a little ratchet, which is fully functional. This prints in one piece, so there's no assembly required. It will do 3 inch-pounds of torque, which is the specific amount that they needed. And it was just a really easy way to save on a rocket into space. Now sometimes, moving on from just plastic, you do need a little bit stronger. This right here is an example of a printer that can continuously infill carbon fiber, which is very strong. It's also very lightweight, and it has a lot of usages. So this two-tone type material here, the white is our regular plastic, and then this grayish color here would have been the carbon fiber. Now this lab is also well known across New York State for being one of the #1 producers of face shields during COVID. The laser cutter in this lab, which we can show you in a minute, cut the plastic out in about 4 or 5 sheets thick at a time, and then the orange part was 3D printed on the 3D printers. During COVID, all the SUNY schools would have materials to do so. We're producing these. However, this lab was the #1 producer, making over a quarter of all of the ones that came out of New York State. So it was very successful and a very good way to learn about the 3D printers and fine-tune to the best production standards possible. You'll also see in front of me this massive tower of folks. These are called benches. This is a benchmark test for our 3D printer, whether it is average size, really, really big, or really, really small. This benchmark test has arches and overhangs and angles and circles and lions and tigers and bears, oh my. This bench sheet is how we test to make sure our printers are functional, whether we just got a new one, we make a repair, we make an upgrade, anything like that. This is how we make sure they're still doing exactly what we want. Now, these FDM printers can do a lot, but there are some things that they're not as good at, which is when we turn to a resin printer, which starts out with a liquid resin that is girded a UV light, whether it's from a laser or a screen, into the pattern. So where our FDM printers I just showed you work their way up, this starts with the bed and works its way down, but also up in the bottom. So coming off the resin printer, you'll get something like this. You break the supports off, you clean the object, and you cure it, and you'll go from this to this. So you can do some really fine and intricate works on there. Stuff for circuit boards and such are examples. And also usable but strong things, such as lighting fixtures on this college campus can be repaired using these clips instead of buying new ones from the company, which is extremely expensive. So now, we're not looking at printing any of these things. No, we're looking at making our prototypes of our cutters. So let's go over to the computer and get that set up. So here on the lab computer, we have a very useful program called Ultimaker Cura, which is what is called a slicer program. As I explained earlier, the way our objects are made is it works layer by layer, up and up and up. So you have your CAD file, which is a three-dimensional object. It turns that into many, many, many very thin two-dimensional objects and prints one on top of the other until your object's complete. That is what this software turns it into, from a three-dimensional object to a bunch of very, very small two-dimensional objects. So the first thing we're going to want to do is pull our objects in. Which you can see right here. I have already downloaded them as an STL, which is standard Tessalon language. This is a very easy to use type of file for the slicer, so it's the best to get. You can get this out of any major 3D modeling program, such as Fusion 360, SolidWorks, Autodesk Inventor, things like that. So you'll see that there's some overlap for parts, which we do not want. That would print them together. That is not good, so you can just move them around so they are separate parts. As you can see, nothing is touching, which is good. So over on the right here, we have general settings, infill density. So if you have any solid part of your design, it will not print it solid unless you tell it to. It will fill it in a certain percentage. So right now, anything solid in our part, it will fill in 20%. We want this to be pretty strong, so I'm going to up this to 50%, which should be more than enough for what we need. There are some thinner parts that will still break. However, 50% will be good enough for the rest of what we need to do. Infill pattern, we're going to leave this on cubic. However, there are some infill patterns that will be stronger in some applications and not as strong in others. Cubic is fine for our needs right here. We do not need any supports. So the way the supports work when 3D printing and what they do is, as you saw on that resin print earlier, those lines that went up and down on the head bust, those supports were used to print the part of the object that was essentially suspended in thin air, because we cannot print in thin air, not yet at least. So there always needs to be a part connecting it to the print bed, the build plate. So in this case, we do not have any major overhangs that we have to worry about. The software is really nice where it will highlight them in red. However, printers are capable of doing some bridging, because as that filament comes out of the extruder, it cools down very rapidly and starts to harden. So there is a certain amount of overhang you can get, and from experience, I know that this will be perfectly okay. So adhesion, we also do not need. This will create extra layers of filament around the object to help hold them onto the bed. However, we already have a lot of surface area on the build plate, so we are perfectly okay with that. The other things that we have to look at are the actual settings for the 3D printer. So I'm going to look at the custom. Our layer height is 0.2 millimeters, which is perfectly okay. That means each one of those layers I told you it splits into will be 0.2 millimeters thick, which is a good standard for this. I'm going to look at the material and our printing temperatures here. So it defaults to 260, which are general PLA settings that will melt it, that will hold it. However, we are going to want to change this to 210 degrees Celsius for the extruder. And we're going to want 65 degrees on the bed. The reason that the bed is heated is because as things rapidly cool, they can also contract, which we do not want. When things contract, they warp, and that creates a non-flat finish. So the bed is heated to help slow that cooling process, at least on the first layer, because if it's on the bed, there will be no overhang, so you don't have to worry about it cooling instantly. Once we adjust that, everything else is preset because this is one of the lab computers. So I can see my object is all set. These settings have been altered. I'm now good to hit the big blue button to slice it. This will turn it into layer by layer by layer organization. When I go to the preview tab, you can see the lines, the layer lines. If I zoom in, each little line represents one width of the extruder. The yellow represents your infill, the red would be walls, and the green outer walls, and the green would be inner walls. So it's pretty cool to see. I can move this up and down in layer so that you can see how certain layers work. Here's that infill pattern I was telling you about. As you can see, it will not print solid. However, half of that is filled in this cubic infill pattern. So, and if you're curious about exactly how it will work, you can hit the preview button and you can watch the extruder do the exact pattern that it will do when it gets on the 3D printer. What we have done by slicing it is created a G-code, which is just a program for the 3D printer to follow when we send it onto it. So that is what this Save to Disk button will do. However, we still need to put the disk in. So let's head over and pick a 3D printer. So I'm going to go with this printer 4 right here as our example. This printer was recently repaired, so this will be a good test to see if it's working properly. So the printer is already on, however there is a power switch right here. So you flip that to the on position, or the line with the circle, and then on the front of the printer right here, you can see that there is an SD card slot. You click it in and you pull out the SD card, labeled with the printer that it came out of, because this lab is very organized. And I can check right here before we even begin that there is not any kind of a tag in here that says the printer needs repair or is reserved. So we are all set to use it. So let's bring this card back over to the computer. So we are at the computer, our file is sliced. We also have a time estimate right there of 2 hours and 11 minutes and 29 grams of filament used. So plugged into this USB extension is an SD card reader. I can just go ahead and plug that in. And those are available for anyone who likes to print in this lab. This is open to all students and faculty who would like to learn. So when this notification goes away, you see I now have the option to save it to the removable drive, which is this SD card. I can click that button and it's saved and it tells me what it named it, which is Creality S1 Pro Frame.G-code. And I can eject that drive, and it's on this SD card now, ready to go in the printer. So let's head back over. So I can now click this back into the printer, like so. The screen will reload and we're all set now. Right now I can read the label on this filament right here, see it's PLA, and I can see that it's black. That's a little bit too boring for our very exciting team, so I'm going to switch that color out and show you guys how to do that. So on your screen right here, this has all the printer controls and interface. You can go to the Ready tab, and then you'll have some axes moving options and stuff. We don't have to worry about any of that right now. We're going to go to the Manual button and preheat PLA, because I can see that PLA is what is currently loaded in the printer, so we want to preheat it for that. Then I can go back to the home menu where I can monitor temperatures. So now let's look at what some color options are. Our team ended up selecting PLA as our material of choice because of its qualities such as print quality, temperatures, and price. So let's head over to the filament cabinet and pick something out. After this very long trek across the room, we come to our filament cabinet, which is organized so that PLA is on this middle shelf. These are all of our partial rolls, so as to not waste material, let's pick a partial roll. For me, I think our team likes green because we are saving the environment by using an already open roll. So let's head back over to the 3D printer. Now, much like you've already seen myself get decapitated many times in this video, we're going to do the same thing to this filament on the end. So you will see right here that the filament has the stringy and this ball on the end of it, That will not let it go into the extruder very easily. So if you cut that end off like so, you'll see it's nice and smooth. It'll go into the printer more easily. Now, there are other ways to do this. The suggested method is to use the diagonal cutters or flush cutters, depending on what your choice is. These come with the printer. However, we like to have a little bit of fun on our team. So I can look at the printer right now and see that it is at 210 degrees on the nozzle and 63 degrees on the bed. All we care about is the nozzle temperature for right now, so we are ready to extract this filament. All right, so let's extract this filament. So if you look at the nozzle right here, you'll see the filament goes in through this hole and there's this little tab. If I hold this tab over to the left side, it releases the tension on the filament, which allows me to grab it and pull it right out. You can see it has that same end on it that I already cut off of the other piece. A little bit stringy, but that is okay. This spot right here where it runs through is the filament runout sensor, so if the printer runs out of filament, it stops printing. I can just rotate it out like this, pull the spool off the printer, and my end is free. Thread this through one of the holes on the filament spool because we do not want it to get tangled up and loose because that does not make for great print quality. This will go back in the cabinet now. All put away, nice and tidy. Let's head back to our print. So after that marathon, we can now take our new spool of filament and put it on the same filament spool holder like we had. It's important that we have our filament pull this way as it goes in the extruder so that the spool rolls easier, once again increasing your print quality. So I can unfeed this piece of filament from these two holes on the spool, making sure to keep tension on it like so. And then I can just put it right through the filament runout sensor where a blue light turns on to say that it detects filament. I'm going to just pull this down a little bit more, keeping my hand near the filament so it does not keep spooling. And the same thing I did last time, I pulled out on the tab, put it in the hole, and I just pushed it a little bit. You'll feel a little bit of resistance, but it will keep going in. If you look at the bottom of the extruder, you'll see a little bit of filament coming out that is actually starting to turn green. So we are going to continue doing this until the filament comes out fully green. Which, as you can see right here, this looks pretty green to me. So our last step before we start the print is going to be to clean the print bed. So this right here is a smooth PEI bed, which when it heats up becomes a very glue-like texture. It helps hold the print to the bed, cure it nicely. But this does not always stay clean, which is why we take our isopropyl alcohol wipes and clean it before each and every print. So you just unfold your wipe, run it across. Even if the bed is warm, it is suggested that you do this when it's cold. However, for this print, it should be fine. So the print bed is nice and clean now. Pick up our garbage and throw it out in any local garbage can. Now our filament is loaded, which is our material to print out of. The bed is ready. The file is on the SD card. We are ready to print. So after a few presses of the print button, selecting our part and then hitting the play button, you will see the printer start to print. The process that you see right now is the bed leveling process, where it uses the probe on the left corner to detect the exact height at which the bed is. This way it knows where to put the nozzle as it starts the print. The process you see on the left right now is called the filament wipe, where it makes sure that there is no extra filament on the nozzle that will get in the way of completing the print. And now it is doing the outline around where our object will be. So we're now going to let it be, and we'll come back to it in about 2 hours and 11 minutes. All right, so just grab a bite to eat for a few minutes, and about 15 minutes as I start the print. Let's take a look and see how it's doing. No! That is not good. I'm so getting fired for this.
First off with this project, I'd like to discuss our timeline of the work we've done so far. Week 1, we gathered inspiration from other cutters, scissors, and various things that are similar to our end goal. We took a look at them and brainstormed which parts we would like to use for our final project. For week 2, we decided it wasn't enough to just take a look at our inspiration, so if possible, we went and tested out in person. And for the ones that we didn't have access to, we looked up videos online and really took a look at if it did what we would like. For week 3, we sat down and started working on our design for the product. We really wanted to put a lot of thought into it before starting our prototyping, just to make sure we reduced a little bit of that trial and error period. First, we will be discussing weeks 1 and 2. We will be discussing these together because these two worked hand in hand in deciding which pieces of technology we were going to utilize in our design. Initially, there were several types of blades and cutting methods that we did not draw inspiration from. We brought them up, but before even going to the testing phase, we realized this would not work for our project. One of them being just a handheld single blade, as that didn't apply even pressure, we couldn't measure anything, and overall would not work for what we were doing. Secondly, a type of rotary blade. While that is a bit more even, it doesn't cut at the same time. It only does a little piece at a time, and again, could not measure, only did a thin piece, would not work for our project. And lastly, we thought about some more complex tools and cutting machines, and considering that we are only 3 students, it would be difficult to build a machine like that from scratch in a semester. So we went for more of a handheld, smaller device that we could use for this project.
We looked at several designs when getting inspiration for our own design. One of the devices we looked at was a paper cutter, like this one. Unfortunately, this paper cutter does not apply pressure evenly, so by the axis where the blade moves, that, like, the closer to the axis, the sooner that part of the material is going to get cut.
In this clip, we are testing out the paper cutter we just showed, and as you can see right here when I press down, it doesn't press evenly, so the paper comes out slanted, and it only goes a little bit at a time, and it just doesn't work very well for what we're looking for.
We also looked at these kinds of paper cutters. This kind of paper cutter does not apply pressure evenly as well, and only applies pressure close to the blade. And it is also meant for thin material that is not cylindrical.
This right here shows a very early sketch in our design process that was based off of several other ideas similar to like a handheld version of the paper cutters we have shown. But quickly after taking a look at this, we decided that due to how the pressure, like we discussed in the other two, starts in the middle and works outwards, it wouldn't work in a uniform stress cutter. Just because we want to get the most even cut possible, and this wouldn't work for that. This, compared to whatever our final project ends up being, though, will be a great comparison in the evolution of our design over time. Another device we looked at is a wire cutter. We were just brainstorming different tools, and we figured this could be useful. This is more what we're aiming for in terms of quality. Obviously, we might not get there in a semester, but it would be ideal to have a product that could work well and hold up over time. This also is useful in terms of what materials we were aiming to cut. Oftentimes it's used to cut wires, which are cylindrical, much like the materials we want to cut, just on a smaller scale, and a lot of metals as well. The only cons with this is much like a lot of the other things we've discussed, like the paper cutters, and with like normal scissors, it has uneven cuts since the pressure is strongest towards the inside of the device. The next thing we looked at was a wire stripper. This gave us more of an even, rounder cut since it's used to cut the outside of a wire, get the rubber casing off, and we figured this could be a useful addition in terms of trying to find things that more easily cut cylindrical objects. The cons for this is, unfortunately, while it is closer to being an even cut, it's still a bit uneven since there's only 2 parts that it comes from, and it doesn't cut all the way through. The next device we looked at was an egg topper. This is closer to what we are going for with our design. When you move the handles closer together, it comes in around the egg to evenly impact most of the sides. But as you can tell from it, it's jagged, which works perfect for what it's meant for, but it wouldn't cut. So ideally, we'd use a similar design to this, and we'd add blades in there so that it would cut our object and do what we were intending for. The next device we looked at was a 3-blade cigar cutter. This is very similar to what I described on the last slide, where since as you move the handles, the blades come in evenly to cut the object, in this case a cigar. The pros of this is that 3 blades is more even cut, so with our project we'd ideally be going for at least 3 blades. But the cons are, like I said, if you go for more blades, it's more of an even cut. So we could add additional ones just to make sure that our device is as accurate as we can get it.
Here's our first device that we utilized and experimented with. It was printed out of PLA material and used a singular razor blade, so it also did not distribute the pressure evenly. This device was a very good launching off point because it was quick to make since we 3D printed it and helped us experiment with more handheld ideas. But this device also does not cut evenly, so we are not able to use it in our final design.
So this is another example of a cigar cutter that we looked at as a team while looking at designing our own. Here, I'll show you how it works. We have the base right here. This is just the main body of it. There is a slider that takes a utility knife blade or a razor blade, depending on where you're from. They have all different names. You can see the 2 gaps right here. The 2 gaps right here fit these 2 notches on here. Same with the right side here and here. They go right in that track and they slide back and forth with the utility blade, which will stick out and cover this hole, which you'll see just in just a second. The cover will go on top and create the entire mechanism. As we go over here, you can see it fully assembled, where there's the slider right here that will move in and out. There is the hole and there's the razor blade across it. So let's take a look at how it actually works. So here on the assembled one, once again, you can see that there is the blue section highlighted, which represents the interior section I showed you on the previous that moves on that track back and forth, only this time there is a utility blade with it. So it goes out like this and allows this hole to have a piece of material inserted in it, or in this case a cigar. And then it will slide right back in until this comes flush against the surface while the blade makes its way across that hole. Let's watch that again right here. So you can see as I move it across, it will slice any material that comes in its path. So this is an example of a cigar cutter, which once again, we considered it in part of our design. However, it is nowhere near a final product because as you can see, there is only 1 blade, which only comes from one side, which is not what we were looking for in a uniform stress cutter. This is just a more guided version of a paper cutter, as we've looked at already, which we already established something like that is nowhere near what we are looking for. So we were able to take the idea from this to have some kind of a sliding track with blades though, which a lot of things nowadays have, but it is also important to note that we did physically create this object. We 3D printed it out of PLA filament. We made this on an FDM printer, which was shown previously, and it worked for its purpose as a cigar cutter with the utility blade added in just from a regular pack of utility blades. Nothing fancy. It's a really budget-friendly option if you are in the market for a cigar cutter. However, in our case, this is not a uniform stress cutter, which means we were unable to use it. So we learned a lot from it though, so it was not pointless. And trial and error is our best friend.
The 3D printed version of the 3D model that you just saw, unfortunately, ours broke before we could get a recording of us testing it, but I figured we could still commentate on how those work and how effective it is. I have an example video I found on YouTube, and as you can see here, it has a singular blade. Sometimes the one there has a second one on the bottom, which is a little more efficient than ours. But as you can see, it's only got those blades. And then as he gets to it, he's going to rotate the cigar so it can cut it, because those don't cut evenly. So that's as close as you can get to a solid cut with like several blades with one of those. You have to rotate it, so it's not as efficient. With this example right here as well, you can kind of see how he has to rotate it slightly again. And also, once he cuts it, it's gonna have some things fly out. It's not gonna be as smooth as, let's say, something with 3 or 4 blades coming in all at once, applying even pressure all around. See, right here, it's gonna like pop, and you'll see it's a little like jagged as well.
Our plan is to take something like this and add more blades to it, possibly to have around 3 or 4 blades total, to more evenly apply pressure to the material we are cutting. Our plans for the future is to design a cutter based off of these ideas by picking and choosing what we liked from each device we looked at, and incorporating ideas from that and mechanism, and incorporating design elements from those devices and putting them into our own. Like using the idea of a cigar cutter as our major inspiration and taking elements from it, like its tactile size, and putting it into our own design. We also plan to experiment with different materials for both the body and possibly even the blades of our design. While PLA is very good for rapid prototyping, it is very easily broken, and we would like something that is a little stronger for everyday wear and tear. We also want to experiment with the number of blades that we use in our final design to see which is the most efficient and which ones take the most stress off of them so they last longer.
Alright, so on the screen here, you guys will see an example of our current prototyping status. It may not look like much, but this is where we're at right now. So based on some of the designs that we've shown you, the designs that we've looked at ourselves, we've decided to make this universal stress cutter design. So the way that this works is similar to the other cigar cutters and things that you've seen. There's a body to house blades. There is a hand crank on the top right here. That is the circle that you'll see. There will be a handle on that. It shoots out to this arm, which will not go this far out, but just for demonstration purposes it does. Goes back into the object, and then on the end there will be a blade. So this crank, you'll have a quarter turn of motion because there'll be 4 blades, one going on each side through a slot right here. The 4 blades will come in and uniformly apply pressure and ideally cut our material on the inside. We are looking into other methods of securing our object right now because, as you can see, we don't get much clearance on our way through, but that will come with time. We still have not fully decided on what size material we will be cutting with this and other things similar to that. Regarding materials, the black part we are planning on doing plastic housing because this part will not take any kind of strength other than the hand crank that will be mounted to it. That is the only thing we have to consider, so that will come with our prototyping experimentation phase. The hand crank itself and going out to the arm and down here will most likely remain another type of plastic. If we need strength, we can possibly infuse it with carbon fiber. However, not all of this needs to be some form of metal or super strong material because we are not going to put that much stress or that much weight on it. The idea of a universal stress cutter is to complete the cutting in a uniform way that also reduces stress on the blades and also all other components that are involved. And then continue along this blue line right here. This will go from some form of plastic to our actual metal. So along our cutter, it will turn into the metal blade that will cut the material right here. And keep in mind there will be 4 of these on the outside. Just for demonstrations purposes, there are only 1. So the 4 of them will move in. They will meet at a predetermined position on the inside of where the object being cut would ideally be. Once again, this depends on what we decide our material size to be. We're looking into roughly the size of a cigar right now because that is what a lot of people in professional industry tend to base it off of. But this is our current example of our prototype, which will be in production really, really soon.
Thank you for watching our video.